Hi. Today I'm going to be explaining how to do homework number 11. I'll have this going in the background. That's what it's called. Some nice music. Just a little bit loud here. There we go. A little bit lower. Anyway, okay. So this one is not anywhere near as hard as I think most of the ones we've been doing. It looks like people are actually passing it, which is nice. This is mostly just really light application of what we've been going over recently. We didn't do a whole lot of any of this in class, so we're not as practiced doing this as we maybe should be. But overall, I'd say this is not too hard. It's actually pretty easy. It's mostly just this is the right answer and this isn't because this thing we talked about in class. So this shouldn't be more than like 30 minutes. It shouldn't be an hour and a half like the last one was. That one was long. It took forever to upload. Okay, so let's just start with number 1. Oh, let's get our Excel, because we do have to do math for some of these. Excel will be nice. Just open. Blank version. There we go. Okay. Number 1. Which of the following statements is not consistent with the kinetic molecular theory? Remember, the kinetic molecular theory is just a theory that I don't remember. It's basically just saying that gases work the way we expect gases to work. That's kind of how I remember it. It's basically saying gases are there and they're floating around, little molecules in there, that sort of thing. I just want to see what it says, just so I'm not saying anything incorrect. Kinetic molecular theory, gases are discrete molecules. They're far apart at normal temperature and pressure. Volume gas molecule occupy is very small compared with the container's volume. Gas is mostly empty space. Gas molecules are always moving randomly with random speed and random directions, but their movement is linear. It's not too complicated. So, which of them is not consistent with the kinetic molecular theory? Let's see. Except near the finishing point. The attractive forces between molecules of a gas are very small. This is true. Collisions between the molecules of a gas are elastic. So that's another thing. I didn't actually mention that. Here it is. I have it right here. Yeah. Why did I read that? I don't know. Anyway, let me read it now. I missed 3 and 4. The points on the kinetic molecular. Collisions between gas molecules and other gases or the wall of the container are elastic. Basically, you have the box. You have all the gas in it. It's all moving around. It has temperature that's more than 0. Unless you have some magic box. Because right now I don't think we can actually do that. Basically, if you have this box, it's not going to move. All the gases, their collective movement, their pressure, that's what that is, temperature, all more or less the same thing, in this case anyway. It's moving in all directions, so even though it hits the walls and the other gases, the total, the box isn't moving. The box is staying still, and all the gases aren't slowing down or speeding up. It's elastic. So when one gas molecule bounces off another, or bounces off the wall, it's going to bounce off, and it's going to have the same amount of kinetic energy as when it hit it, or the other gas molecule. That's what elastic means. Also, aside from collision, gas molecules do not exert force on one another. Rather, gas molecules travel in straight lines with constant velocity. This is just saying that an ideal gas, it doesn't affect other gas molecules. In an ideal gas, there are very small. The attractions between the gas particles are very small. So the more polar and the larger gas molecules are, or if they have hydrogen bonding, or if they're ions, the less true this is, unless it's really high temperature and really low pressure. And it means that they have really high boiling points and melting points and stuff. Volume carried by the molecules only of a gas becomes significant. So 4 is okay. So 4 is wrong. Let's go on to 5 to explain it. Get into it, I guess. Yeah. So what number 5 is saying is that, so like it was saying, gas is mostly empty, but when you get close to the liquefaction point, the gas is starting to get attracted by other gas, and its pressure, its volume is decreasing because it's starting to condense. So there's actually less and less empty space the closer something is to liquid compared with the gas. And then when you go from a liquid to a solid, there's even less empty space, I think. The reason number 4 is wrong is that this is the opposite. So when you have really low pressure, the volume occupied by molecules of a gas actually becomes less significant because it spreads out. So lower pressure means higher volume, PV equals nRT. So PV are on the same side, right? So P and V are on the same side. So when P goes up, V goes down. But when V goes down, you have a low pressure, the V goes up. That means that the molecules are further and further apart. And the further apart they are, the more empty space. And if there's more empty space, the volume occupied by the molecules is actually less significant, not more. So 4 is the wrong answer, which is what it's asking for, which is not consistent. Number 2, plot the Maxwell distribution for the same gas against temperature shows that. Let's see what this... Oh, okay. So what this is talking about is... So they had graphs, Maxwell distribution. I don't really know how to explain it, so... Distribution. Yeah, that thing. So basically all it's saying is that... So this green line represents a gas that is going that has a really high average... So here it shows this one better. So as we can see, this green line, really high speed, really high temperature, high average velocity. This T has a lower average velocity. So it's talking about this graph right here, right? And then you also have it for stuff, so for mass, the higher a mass, the slower its speed. So yeah, but let's just go back to this one because this is a really simple version of it. So we can consider this to be a low speed, low temperature, high mass. And this can be our low mass, high speed, high temperature particle. So for number 2, so at high speeds, so if we look at high speeds, the average, more particles are further away from the average, not closer. So this is incorrect. As the temperature increases, a high proportion of molecules have very slow speeds. That's the opposite of what this means. So there is a proportion, but most of them have higher speeds. Like the number that's more or less than the average are equal, so a high proportion is not correct. I wouldn't describe it that way, at least. As the temperature decreases, the spread of speed widens. So that's what happens when the temperature increases, not decrease. That's incorrect. As the temperature decreases, a high proportion of molecules have very high speeds. So it's just like this one. If you're comparing if you say very high speeds referring to the average speed at a temperature, it doesn't make a whole lot of sense to say this. If you're talking about high speed, like compared with the other graph, sort of, but it doesn't refer to another graph, so we just have to assume it refers to the average, and the exact same number of molecules are going to be over as they are under the average. Number 5 is correct because, as we can see, this lower temperature, the average, more particles are very close to it, whereas at this one, they're more spread out. The graph widens, so it gets further and more molecules are further and further away from the average speed. So more of them have like a speed that's not... So this is plus minus 100 zone right here. So from here to here, there's about 1, 2, 3, 4, 5, 6, 7, 8. There's 8 in here. But as we can see with this one, there's like 16 in here. So much more of the gas is in this speed range than in this one. This one is much more spread out. They're a lot further away from the average. So number 5 is correct. Number 3. At a temperature of 300 Kelvin, all gases like helium, argon have something average kinetic energies. Okay, so notice that this isn't saying average speed. This is saying average kinetic energy. So what it means by average kinetic energy is it's the speed times the mass, right? So it's I think it's half mv squared or something like that. It's momentum, I think. But basically what it's saying, yeah, that's what it is. Kinetic, KE equals, here, let me find it. It's in here somewhere. My homework 10 has like pages and pages of work. Jeez. Where are you? There we go. Kinetic energy average equals half mv squared. So it's half times mass times velocity squared. So because these have different masses, they're going to have a different speed in order to have the same kinetic energy, because kinetic energy is equivalent to temperature. So they're going to have the same, not different. It's going to be the same. So 6, 4, 3 could be right. And then the next one, and they have something. What does it say? The same diffusion rates, the same average velocity. So they won't have the same average velocity. They should have different average velocities. The same diffusion rates. So diffusion rates are dependent on average velocity, not on kinetic energy. So it's actually going to have different average velocities. And as we can see, that's right. Go on to number 4. So for number 4, what we're doing here is, so in notes from like, I think it was Thursday. Do I have it here? No, yeah, it's on Thursday. So, or maybe, no, I think it was Tuesday. I think it's last Tuesday actually. So what are we doing? It's speed and temperature. Okay, here we go. So for this, we have V. So we have velocity A. We're just gonna say VA. Let's say lowercase a. There we go. VA over VB is equal to. We can put equal. Let's put it here. Equal to the square root. So if we put it in there, then it's gonna get mad at us. Let's just put it here. It's equal to the square root. So we're gonna have to have parentheses. Oh my, that's so annoying. I haven't used Excel in like a week already. I'm not used to it. T. So this is our temperature A, and then so it's to the, I don't know how to do up and down, so I'm just gonna do to the half. Well, you know what we can do? We can TA over TB, and then this half is going to be square root. This is going to be to the power of a half. I don't know how to put it in the right place, so you're just gonna have to pretend. Pretend this is a square root. So what this means is that the velocity is directly proportional to the square root of the temperature. So what we do is we have 25, which if you add 25 to 273, you will get 298 Kelvin over, and this is going to be our VB. We don't know what that is to find out. Equals. And then we just put in our oh wait, that's, dang it, that's velocity. I put the wrong number in there. 640, yeah, 640. Okay, and then VB equals, and then it's going to be, how do we do square root in this? I don't know how to do square root in this, but I'm just gonna like show what the numbers are. So TA is going to be the temperature A, so it's gonna be 25, so it's gonna be our 298. And then we divide that by TB, which is going to be 273 plus 100 is 373. And then it's going to be to the half power. So when we do the math, it's going to be 640 over the square root of 298 over 373 equals velocity B. So I don't know how to do square roots, and so we're just going to use Desmos. So all we do is 640 divided by the square root of, what was it? 298 over 373. Okay. 298 divided by 373. And we get our new speed of 716. Now, you don't need to like think about it too hard if you just do the math, but as we can see, our temperature went up by 75 degrees, so our speed, our meters per second, is going to increase as well. So it increased a little bit. That's because it's not directly proportional. It's directly proportional to the square root of the temperature. So it's going to go up by like the square root of 75, whatever that is, and it's going to be multiplied by this. So it's like I don't know how to do the exact math. but you get what I'm saying. It's going up, obviously, and it's not going up by a very obvious multiplier. So you do have to use the equation, or you're probably gonna get, or you're gonna get it wrong, which is not ideal. So it's 5. So in this one, all we're doing is I believe we're just plugging in 329 degrees Celsius into the equation for URMS. So the root mean squared. Here, let me put the equation so we can do this. So URMS, or root mean squared velocity, equals. I really need to learn how to put square root, but for now it's fine. Where is it? There you go. It's, oh my gosh. It's 3RT over M, and then to this, and then to the square root, the half power. So you squared it. So what this means is that your root mean square velocity, which is equivalent to your average velocity, is equal to the square root of 3 times r. That's our r value, but it's going to be different because we're using different what's it called? We're using different units. Sorry, I just forgot for some reason. We're using different units, so instead of being 0.082, it's now 8.314. Yeah. And it's going to have different units itself as well. So we'll go over that in a quick second. But first, this temperature is still in Kelvin, and this is molar mass. It's not mass, it's molar mass, and it's in kilograms per moles. So you're going to divide it by 1,000. So just to show, so URMS is in meters per second. 3 is just 3, and then our R value is now 8.314 J per mole times K. And I'll explain in a second how all the units work out first, and then we have temperature just in Kelvin, and then this is, like I said, this is molar mass in kilograms per mole, which is kind of weird, but there's a reason they're doing that. So how do these units work out? So remember, this is URMS. URMS is in meters per second. How do we turn K and kilograms per mole and joules per mole K into meters per second? Now, how we do it is the J, actually, because J, 1 joule, if you remember, is equal to 1 kilogram times meter. I don't remember how to do the squared, but right, you can do that's what it is, 2 meter to the second power over seconds to the second power. And then, because it's square rooted, okay, so yeah, that's how you do it. There we go. That's not super nice, but it's good enough. So when you square root these two squared, they become just a single unit. They're not squared anymore. So that's how we get it. So let's go ahead and cross them out. So we see our R is multiplied by T. So it's K over 1 times 1 over K. So that K is crossed out. Lose our K. And then on the bottom is divided by mole, and we have divided by mole. So we divided by mole by divided by mole. I know, it makes a lot of sense. So we divide by mole. I am kind of butchering this explanation, which I typed out. I don't really care. And then we just have joules, and we have kilograms, we have meters per second. So this joule, we break it down into kilogram times meter to the power of 2 divided by seconds to the power of 2. And then this kilogram is on the bottom and this kilogram is on the top, so they divide, and that goes away. That goes away. And then we have meters squared per second squared, and then we divide, and we square root it. So then that that goes away. and we're left with meters per second equals meters per second. That's just how all the units work. If you need to get the units again, just rewind. I'm not gonna. I can, but I'm not gonna mess with it too much. We just want to we want to do the math. We don't want to be here forever. So we can go ahead and put our numbers down. So we have 3. So we have 3 times r, which is 8.314, times our T. Our temperature is 273 plus 329. I actually forgot to do this, so I got it wrong the first time. That's fun. 602. So we have 602 Kelvin. And then we divide that by our molar mass of fluorine gas. Fluorine gas is diatomic, so it's 19 grams per mole. Times 2 is 38 grams per mole. And then we divide that by 1,000. So it then becomes 0.038 kilograms per mole. So that's fun. And then, of course, this is all square rooted. So let's put this in parentheses, and then power of a half. So we're going to go ahead and plug this into Desmos. We could probably just, we can just copy this, I think. That's not what we want to do. This is the power of, actually, let's get rid of that, and we can just do this. Yeah. It doesn't want to do what I want it to do. How annoying. And we can get rid of this. There we go. So that gives us a speed of 628.6, which is the right answer. That wasn't too hard. And then this is a similar calculation to this. No, actually, sorry, it's not. So we actually do this differently. So we can get rid of this. So that's actually what I meant to say is it's like this, but it's a mass and speed instead of temperature. So just like with velocity being directly proportional to the square root of temperature, velocity is inversely proportional to the square root of mass. So let's get that because I want to. There we go. I found it. Here we go. So instead of, let's fix this with our to the power of. And so instead of this, so with mass, it's not going to be mass A on the top. It's actually going to be mass B on the top and mass A on the bottom because it's inversely proportional. So it's just a slight difference, but you do have to remember that. And basically what this means is that instead of the velocity going up when the mass goes up, the velocity goes down when the mass goes up. So that's not too difficult, I think. So we have our velocity A and our velocity B. And what we're going to do is we're going to plug in so hydrogen can be A and oxygen can be B. So oxygen will be 32 because it's 16 times 2. And then that's going to be over hydrogen, which is H2, so it's going to be 2. And it's just going to be the square root of that. And we can just plug that in really quickly. 32 over 2 is 16. And the square root of 16, square root of 16 is just 4. So hydrogen is going to be 4 times. So as we can see, the average speed, hydrogen molecules have an average speed that is 4 times of oxygen molecules. Excuse me. Whew. Allergies are not kind on occasion. So so because hydrogen is so much lighter, it's 16 times lighter, but it's the square root of that faster. So it's 4 times faster than oxygen molecules at the same temperature. And it has to be the same temperature because the same temperature is where they have the same kinetic energy. So as we can see, 6 is 1. Given the gases, put them in an increasing rate. Okay, so the ERMS, the root mean square velocity, the average velocity, and the average kinetic energy are all directly proportional, as well as the rate of diffusion. So increasing, so the lowest is going to be on this end, it's just going to be the lightest. increasing. Oh wait, no, sorry, I'm dumb. The fastest is going to be on this end. This is going to be the fastest. So this side's going to be the lightest. Sorry, brain fart. So HE is the lightest because it weighs 2. And it's just the opposite of 1, which increasing means that the fastest rate of fusion is here. And the smallest molecule is going to fuse the fastest. And you can just think of a small hole, and then you have to have molecules go through the hole. And the smaller the molecule is, the easier it goes through, just because it's more likely to fit through and not hit the sides and bounce off. So number 3 is right, just because the heaviest krypton is like 38, 83. I was opposite of it. That's right. It's 83, and this is 28, and this is 10. Thereabouts. Actually, I don't know how much. 20. I am just completely off. Anyway, hydrogen on this end and krypton on that end, and that's why that's right. It's because it's lighter and it's smaller. Calculate the ratio of the radiofusion. So this one I'm actually a little bit confused on. So because its velocity is directly proportional, we can use the same thing here, and it's HE, which is also 2, but CO2 is actually, it's 32 plus carbon, which is 12, so 32 plus 12 is 44, and then we do the square root of 22. We're because it's directly proportional. But oddly enough, so this is how much faster HE should be. But we don't want that. We want the opposite of that. We actually want 1 over that. So 1 divided by... it just doesn't want to do what I want it to do. It just doesn't want to. Then we divide that by that. So as we can see, this is 0.213. Maybe there's like a specific equation for it, but the only one that's even close is 2, and that was the right answer. So I don't know. This one's I'm a bit confused on, but I think they just rounded it really, really hard. I don't know why. I don't really get it. Which of the statements below is false? Let me find. So the van der Waals equation is what it's referring to there is if you remember, the A and the B for the corrective Puvner equation. So P plus AN squared over V2 times V minus NB equals nRT, and that's for corrections. We haven't used it at all, but it's talking about that here. So A is generally attraction, and it has to do with the attraction between molecules, and B generally refers to the size of the molecules in question. The smaller A and B are, the more ideal they are. So the B factor in the so it's asking which one is false. Should be larger for HE. So this is false. The B factor gets bigger when something's larger. Cl2 is much bigger than HE. So the B factor should be bigger than for Cl2. So this is false. I don't have to check the rest of these. I did earlier, but this is correct because HF has more attraction between each HF because it's ionic. It has hydrogen bonds. It has a dipole moment, and HE is just van der Waals. This is correct. I already talked about that up earlier. Gases approach the liquefaction points. When things lower in temperature, they become more liquid and then more solid. That's correct. Pressure increases because it's getting closer together. The volume is decreasing, pressure increases. At really high temperatures, so further away from being a liquid, the more ideally a gas behaves. And then an ideal gas has an A of 0 and a B of 0. That's all true. So it's going to be 1, is the false statement. So these are just some A values. So this is referring entirely to attraction between molecules, right? So the higher it is, the more attraction between molecules. And then it's saying which A value should be assigned to CO2. So right away, Ne has the least because it's a noble gas. It's one of these, Ne. They have only LDF. They have very, very little attraction between each atom. They're not diatomic. So it's going to have this. And then we can look and we can see CH3CN is polar, whereas CO2 and CH4 are not polar. So it's going to have 17.58, these two are only going to be van der Waals. Or sorry, is it van der Waals? No, it's LDFs. It's London Dispersion Forces. Van der Waals is something else. Sorry, I'm confusing myself. These are only going to have LDFs, CO2 and CH4, but they're going to be they're going to have more because attraction has to do with size. So the bigger something is, the bigger the A is going to be. But they're very close together. These two are very close. They're only just a little bit off. But you might say, okay, well then which is which? CO2 is bigger. It's not a lot bigger. Well, that's not true. It's like, how much bigger is it? It's like 28 atomic units bigger, atomic mass units bigger. So it is a sizable amount bigger, but it feels like it should be more. This should be a bigger if it's going to, but I don't know. I haven't seen a whole lot of A and B values, so I honestly can't tell. But this should have a higher A value just because it is bigger. So that it does, in fact, manage to be true. This is number 2. So that one's a little bit confusing. We haven't really seen many problems that have to do with van der Waals equations, but they decided to throw some in here. Anyway, so not too hard, just a little bit confusing. Which condition will the density of gaseous argon be the lowest? So density meaning, I think grams per liter. So density is going to be the lowest when the pressure is lower and the temperature is higher. Because the higher the temperature, the higher the volume. So we want our volume to be as big as possible for the lowest density. So we want for the higher pressure, we want for a higher volume, we want a lower pressure and a higher temperature. So we have 1 atmosphere of pressure or 2 atmospheres of pressure. We want a lower pressure, so only one of these will be right. And then we want a higher temperature, so it's going to be number 1. And as you can see, that's correct. And then this is not true. Noble gases are actually closer to ideal gases, so the PV equals nRT equation is actually more applicable. So this is very wrong. Do not listen to this. This is incorrect. And then, sorry. Mucus in my voice box, my throat. It's not fun. I think the gas molecules in terms of increasing and non-ideality. So basically, it's just saying rank them based off of increasing intermolecular forces. So right away, H2 has the strongest because it has hydrogen bonds. This doesn't have hydrogen bonds. This is C bonded to 3 hydrogens and 1 fluorine. The fluorine is not bonded to the hydrogen, so it does not have hydrogen bonds. H2 is the strongest. So it's going to be number 3. Because any of the rest of these saying, even any of these, I mean, also He is here. He is a noble gas. They are the most ideal gases, generally. H2 is here. It's only slightly less ideal. Then there's a non-polar gas, and there's a polar gas, and then there's a hydrogen bonding molecule. So number 3 is correct. But you can just see the H2O and think this is probably number 3. And it is number 3. So these are really just if you like paid attention during class. These aren't too hard. I did manage to get some of them wrong because I used the wrong number, but probably don't do that. Anyway, which of the following statements regarding intermolecular forces are true? Intermolecular forces are attractive forces between regions and yeah. So almost all the IMFs have to do with positive and negative charge density. So whether it's actually being polar hydrogen bonds, or instantaneous dipole moments. I got this one wrong actually because I thought that polar molecules they will have an instantaneous dipole moment. I shouldn't think it mattered. I was wrong. It does apparently matter for some reason, so it's only one. Apparently that instantaneous dipole moment that does very nearly nothing is going to be slightly important. Fine. Whatever. I disagree, but fine. Because you're never going to notice the instantaneous dipole moment in a polar molecule because it's so small compared with the the dipole moment that's already there, that it's barely going to matter. But yes, technically speaking, the electrons are still going to move around and cause a slight increase or decrease in the polarity based off of where they are and where the higher density is. And then which of the following, so basically saying which can form hydrogen bonds, because some of these can't. There's no, so in order for you to have hydrogen bonds, you have to have, you have to have hydrogen, and you also have to have one of the following elements bonded directly to the hydrogen. You have to have nitrogen, fluorine, or oxygen. If you don't have one of these three bonded to a hydrogen, no hydrogen bonds. No NFO, no NFO, no NFO. NFO, do they bond? Yes, the answer is yes, by the way. I couldn't, it doesn't give a, I couldn't really figure out exactly whether it would or not. I just looked it up. I mean, like, yeah. And it does, the H bonds to the O, so this is D. But because none of them only have D, it's actually 4. Some of the other choices are correct. So this one's a sneaky one. Start 4 molecules with flying permanent dipole-dipole interaction. So basically, it's just saying which of these are polar. This is going to be polar because it has one of its bonds is going to be hydrogen, which isn't going to balance out. So 1 is going to be polar, and then 3 is also going to be polar, but 4 and 2 are not polar, so it's going to be 1 and 3. So it's going to be this one. See, that's correct. What types of intermolecular interactions does ammonia NH3 exhibit? NH3 has 3 hydrogen bonds, and then it has 1 lone pair. So it's going to experience everything experiences dispersion forces. Everything experiences well, not everything, but because this is a polar molecule, that the lone pair causes it to be polar. So it does have dipole-dipole interaction. This is N bonded to hydrogen, so this has hydrogen bonding. However, because this is a gas, there's no covalent bonding. But I think it's also ionic, so I don't think it would normally have covalent bonds anyway. But it's going to be 1, 2, and 3. And it can only be, it can't be all 4 because there's an option for that, so it has to be number 6. Yeah. Acetic acid, CH3, COOH, forms a molecular solid. What types of forces hold it in a solid configuration? So, if you can't tell, this is a hydroxide ion, and it's O connected to an H, so this will have hydrogen bonding. Also, this is not nonpolar, this is polar, so it will have dipole-dipole. And everything, like I said, has London. So London forces and dispersion forces, same thing. It's LDFs, London dispersion forces, or London dispersion attraction, or whatever. It's the same thing. You just have to remember its name. It can be London, dispersion, and then, does it have any other ones? I can't tell. Anyway, but those are 2 names for it. It's going to do all 3, so it's going to be 1. As you can see, that's correct. And number 18. What is the strongest evidence for hydrogen bonding? She showed it in class, so if you didn't actually watch the thing, then this doesn't make much sense. But she showed that N connected with H, H connected with O, and H connected with F have very, very high boiling points compared with other hydrogen hydrides, I guess. So it's just hydrogen connected with an element just on its own. It's just hydrogen, that other element. And it showed that at really high boiling points. So it's this one. It's number 4. Which of the molecules with dipole-dipole interaction may be important? So SO2 has, I had to check these because I don't know off the top of my head whether they have them or not. SO2 does in fact have a lone pair. It's polar. CO2 is not polar. O2 is also not polar. O3 is polar. It's bent, just like SO2. It has a lone pair on top of it, or 2. I don't remember. So it's A and D. So it's gonna be number 4, as you can see. Which of the following form? So I'm not really sure it being in parentheses means, but I know that NH2 has N connected with H, which is guaranteed to be hydrogen bonds. so I know number 1 is right. So it's number 1. Which of these compounds would you find only dispersion forces? So already one side of this molecule is going to have a higher electron density, so it's going to be polar. CO2 is nonpolar. We already know that. CaCl4 is not polar. It's just it's carbon surrounded by 4 chlorines, and it's nonpolar because it's in a tetrahedral configuration, no lone pairs. It's perfectly balanced. It's not polar. 4 is polar, so it's 1 and 4. So we find 1 and 4. It's gonna be 8. Wait, it's 9. Oh, I was saying the polar ones, and it's asking for only dispersion forces. So it's asking for non-polar. Whoops, it's 2 and 3. It's 2 and 3. Yeah, lol, I misread the question. Had I done it now, I would have gotten it wrong. Fantastic. I am very useful. Anyway, the vapor pressure of all liquids is the same. No. So it increases the temperature. The only thing that really matters to vapor pressure is temperature. That's it. But different liquids have different intermolecular forces and will have a different amount of vapor pressure at a specific temperature. But that liquid will always have the same IMF once it reaches thermodynamic equilibrium at the same temperature, no matter like how big the container is, I think. But it might take a while to reach the thermodynamic equilibrium, and it has to be in a closed container. But it does increase with temperature because and more temperature means that the more liquid will turn into gas. So 2 is right. And then for 23, this is going over what I was saying. So it's the same liquid, H2O. It's H2O in both. And in container B, so this is a different container. So theoretically, if you put that 1 milliliter, it would have a much higher surface area in B. But the surface area doesn't matter. It's only the temperature that matters. It's the same temperature, so it's going to be the same pressure. You can see 5. There we go. And then finally, so methanol has weaker intermolecular forces, a higher vapor pressure than octanol. So these both have almost the exact same, I can't highlight it, but that's all right. They have the same OH, so they both have hydrogen bonding. So if these are talking about hydrogen bonding, they're wrong. So this one, that one, they're both polar, so that one's wrong. Methanol is smaller, so it does not have stronger dispersion forces. Methanol is smaller and has weaker dispersion forces, and that's a good explanation for why it has weaker IMFs. So 1 is correct. And 1 is the only one that works. Anyway, this one, I went over a little bit of whatever. I've been a little bit sick, so I'm a little bit out of my game, but I hope this was useful. If you have any questions, feel free to message me or whatever. I hope you had a fun time doing this homework, and I hope this video helped you figure it out. I will see you in class at some point when I show up. Goodbye.